Okay, so the aim of this video is to discuss the notion of ring homomorphism and ring isomorphism, and I'd like to start with a motivating example. So in the first example we'll look at the following subset of Z mod 15, and this isn't only a subset, it's a subring. So this is the set of elements 0, 5, 10, and it forms a ring. And we have its addition table here and its multiplication table here. And the thing to remember is that we're doing all of our operations modulo 15. So for example, if I do 10 plus 10, I'm getting 5 because 10 plus 10 is 20, and 20 mod 15 is 5. And same thing for all the other entries on both sides. I'm also going to consider this ring Z mod 3 and its addition and multiplication tables down here. And remember, here the arithmetic is happening modulo 3. So for example, 2 plus 2 is 4, but 4 is equal to 1 mod 3. Okay, so these are our two tables. And what we can do is we can take a look at these tables and notice some striking similarities. For example, everywhere that I have a 0 in this addition table, I have a 0 in this addition table. Everywhere I have a 10 in this addition table, I have a 1 in this addition table. And everywhere I have a 5 in this table, I have a 2 in this table. So there's some striking similarities. It's almost like I've taken the table at the top and relabeled its entries. I can do the same thing for multiplication. So for example, the location of the zeros is the same. So we see that there are zeros up here and there are zeros down here. Okay, everywhere that I have a 10 in this table, I have a 1 in this table, and everywhere that I have a 5 in this table, I have a 2 in this table. So again, it's like I've taken the top table, relabeled it to produce the bottom table. So in some sense, these look like exactly the same structure, just labeled differently. So let's kind of explore this idea a little bit. So after relabeling, the one thing we might notice is that 0 can be matched up with 0, 10 from my set S can be matched up with 1 from Z mod 3, and 5 from my set S can be matched up with 2 from Z mod 3. And after doing this relabeling, we see that these are the same table. Okay, so what's actually going on here? What's actually going on is that there's some function between S and Z3, and the function has the following values. I can map 0 to 0, 10 to 1, and 5 to 2. Right? So I'm just kind of writing this down more in a more formal way. So this function is defined this way, and the first thing to notice about this function is that it's a bijection. It's both 1-to-1 and onto. And the other thing to notice is it doesn't seem to matter if I do my operations first and then relabel, or if I relabel and then do my operations, right? And this is true for addition and multiplication. So I can do my operations first and then relabel the result, or I can relabel my 10s as 1s and then do my operation, and I end up in the same place. Okay, so what's actually going on here? How do we capture that? Well, for addition, it's captured by this property that f of a plus b is the same as f of a plus f of b. So this is saying that I can add and then relabel and get this. So this left-hand side is you add a and b and then relabel them with f, or you first relabel them and then add those results. The second is saying that I can multiply a and b and then relabel, or relabel them first and then multiply them, right? And this has to hold for all a and b and s. So this is what's going on here. This kind of captures all the properties of this relabeling. Okay, so now we're ready to define what's called a homomorphism of rings. So we'll say let R and S be rings, and suppose we have a function f from R to S that has the following two properties, that f of a plus b is equal to f of a plus f of b, and f of a times b is equal to f of a times f of b. And this is true for all a and b and R. This type of function will be called a homomorphism, or a homomorphism of rings, because we're talking about ring structures here. And the idea is that this function preserves our operation. So it doesn't matter if I add and then transform, or if I transform first and then add. And it doesn't matter if I multiply and then transform, or transform first and then multiply. Okay, and there's a small subtlety here I'd like to point out, namely that this operation of a plus b, this addition of a plus b, this is happening inside of R. So I'm adding a plus b inside of R, and then mapping that result using f. And what I'm saying is that that should give the same thing as f of a plus f of b, and the subtlety here is that this addition is happening inside of S because f of a is an element of S and f of b is an element of S. So on the one side, the operation's happening inside of R, on the other side, the operation's happening inside of S. And we'll see this in our examples. We also have that the same thing holds for multiplication. This multiplication of a times b happens inside of R, and this multiplication of f of a times f of b happens inside of S, because f of a and f of b are elements of S now. Okay, so what else do we have? Well, if our function is a homomorphism and is also a bijection, we're going to call it an isomorphism. So the function we saw in our first example is an example of what's called an isomorphism. And the idea is not only does this function preserve the operations, it maps the elements in a one-to-one and onto way to S. So it's kind of capturing the idea that not only am I preserving my operations, this is an actual relabeling of R to S. So if we have an isomorphism between R and S, we're going to say that R and S are isomorphic, and we have a symbol for it. We'll say R is isomorphic to S. This will be our symbol. So this is how we're going to indicate that two rings are isomorphic to one another. Okay, and so just a quick review of what a bijection is. A bijection is a function which is both an injection and a surjection. And what is an injection? Well, just a reminder, an injection is a function that has the property that if f of a is equal to f of b, then a is equal to b. So these are injections. They're also called one-to-one functions. And a surjection is also called an onto function. So this basically says that every element of S comes from some element of R. It says if little s is an element of S, then there exists a little r in R such that f of R is equal to S. So this is just a quick reminder, and I'll link a video below to if you're uncomfortable with some of these ideas of bijection, injection, surjection, or maybe haven't seen them in a while, that does a review of some of these. So I'll link this in the description. And one last thing I'd like to point out, there's also a notion of something called an automorphism. And an automorphism is just an isomorphism from a ring to itself. So every once in a while we'll run into automorphisms as well, or we'll run into this terminology. Okay, so now I'd like to do a whole bunch of examples of isomorphisms, homomorphisms, injective homomorphisms, surjective homomorphisms, and all of this kind of stuff. So the first example we're going to start with is a function that takes a real number and it maps it to a matrix. So what does it do to the number a? Well, we're going to define f of a to be a0, 0a. So it takes a real number and maps it to a matrix. And what I claim is that f is an injective homomorphism. So let's prove this. So first I'll start with a and b in R, and what I'm going to do is I'm going to show that f is a homomorphism first. So what I'm going to notice is that, well, let's look at f of a plus b. This is going to be the matrix a plus b, 0, 0, a plus b. And then I notice that I can split this up as a0, 0a plus b0, 0b. And then I notice that this is just f of a plus f of b. Okay, so I've shown that this operation preserves addition. Now I can do the same thing for a times b. So let's look at f of a times b. Well, this is going to be the matrix ab, 0, 0, ab. And what this actually amounts to is the product a0, 0a times b0, 0b. And the subtlety to notice is that on this side, we're using matrix multiplication, and on this side, we're using real number multiplication. So this is what I mean where the operations take place in two different rings. But no matter, this is still f of a times f of b. Okay, so I can say hence, f is a homomorphism. So f is a homomorphism. Okay, so let's prove that f is an injection. So for the injection part, let's suppose that f of a is equal to f of b for some a and b in R. Well, what does that tell me? F of a is really a0, 0a, and f of b is really b0, 0b. And what does it mean for two matrices to be equal? It means all their entries are equal. So namely, their 1, 1 entries are equal, their 1, 2 entries are equal, their 2, 1 entries are equal, and their 2, 2 entries are equal. So we can say, hence, A is equal to B. Okay, so we've shown that f of A equal to f of B implies that A is equal to B, and so f is an injection. The other thing I'll point out is that this is not a surjection. And the idea is there is no A and R such that f of A is equal to, well, let's think of a matrix that doesn't get mapped to. The matrix 1, 1, 1, 1 never gets hit by a function. So this is an example of a homomorphism, which is an injection, but it is not a surjection. Okay, so let's look at another example. So I'm going to look at the subring of M2 of R given by the matrices of the form A, B, minus B, A. And we proved in an earlier video that this was indeed a subring of 2 by 2 matrices. And I'm going to set up a function f from C to K, and I'm going to define it this way. I'm going to say that the complex number A plus BI, where A and B are real numbers, gets mapped to the matrix A, B, minus B, A. And what I'm going to claim is that this function f is an isomorphism. So this subring of M2 of R that we looked at last time is really just the complex numbers in disguise, that these two rings are actually isomorphic. They're the same ring, just labeled differently. Okay, so let's prove this. So I'll let Z and W be complex numbers. So Z is A plus BI and W is C plus DI. And just for convenience, I'll write out Z plus W and Z times W. So Z plus W is A plus C plus B plus DI. So we add the real parts, we add the imaginary parts. And Z times W is AC minus BD, that's the real part, and the imaginary part is AD plus BC. Okay, and the idea is we multiply them out as if we would multiply polynomials, and we take into account the fact that I squared is equal to -1. Okay, so let's try to prove that this is a homomorphism. So if I look at f of Z plus W, well, f of Z plus W is going to be the matrix A plus C, B plus D, minus B plus D, A plus C, right? So the idea again is that A plus C gets mapped to the diagonal of my matrix, and B plus D is the 1, 2 entry, and its negative is the 2, 1 entry. And what do I notice here? I notice that this is just the matrix A, B, minus B, A, plus the matrix C, D, minus D, C. And what is this? This is just f of Z plus f of W. So I see that this function preserves my addition operation. So let's check the multiplication operation now. If I do f of Z times W, this matrix is a bit messy, right? Because I have to take the real part of the matrix, AC minus BD, and put it on the diagonal. So it's going to be AC minus BD and AC minus BD. And I have to take the imaginary part of the matrix, AD plus BC, and put it on the 1, 2 entry, and it's negative on the 2, 1 entry. So I'm going to put AD plus BC here, and then minus AD minus BC here. Okay, so we have this matrix, and then I'm going to decompose this, and it turns out that this can actually be decomposed as AB minus BA times CD minus DC, and we can check that this matrix multiplication works out, right? So we can multiply these two matrices and check that their product is actually that, so this actually works out. And this is nothing more than f of Z times f of W. Okay, so we have that this function preserves our multiplication operation as well. Finally, we can check that this is both an injection and a surjection. So let's check that it's an injection. Okay, so I'll say suppose that f of Z is equal to f of W. Okay, well, what is f of Z? F of Z is just this matrix A, B, minus B, A, and f of W is this matrix C, D, minus D, C. What do we get from there? Well, if these two matrices are equal, then A must equal C. The 1, 1 entries must be the same, and B must equal D. Their 1, 2 entries must be the same. So I can say, so A equals C, and B is equal to D. And so namely, we get that a plus bi is equal to c plus di, or in other words, z is equal to w. So we've shown that if f of z is equal to f of w, then z is equal to w. So we've shown that f is an injection. And we can also check that this function is a surjection. So let's do that. Okay, so we have to consider a matrix. So consider an element of k, so ab minus ba in k. Then, well, we have to ask, is there a complex number that maps to this matrix ab minus ba? So then, we know that a and b are real, so that a plus bi is a complex number, and by our map, we know that f of a plus bi is equal to a b minus ba. Okay, so what have we shown? We've shown that this is a surjection. We've taken a matrix in K and produced a complex number that maps to this matrix. So I've shown that every single matrix in K gets hit by some complex number. So what can we write? We can say that C is isomorphic to K. All right, we've shown that C is isomorphic to K. Okay, so next I'd like to consider an example of what's called the trivial homomorphism. So I'm going to say R and S are rings, and we're going to define a function f from R to S that just takes every element of R and maps it to 0. So this is the 0 function. So it takes everything in R and just maps it to 0. And so the range of this function is, or the image of this function is a one-element set, namely 0. And what I claim is that f is a homomorphism. So this is called, oftentimes it's called the trivial homomorphism. Okay, so let's prove this. So proof. I'm going to say let a and b be elements of R. So then, what do I know? I know f of a plus b. Well, a plus b is an element of R, so I know that this is going to be 0. I know that 0 can be written as 0 plus 0. And then I know that f of a is equal to 0 and f of b is equal to 0. So I have that f of a plus b is f of a plus f of b. And also, I know that since a and b are in R, then a times b is in R. So f of a times b is 0. Well, 0 is just 0 times 0, which is just f of a times f of b. Okay, that's our proof. This is called the trivial homomorphism. This is a very easy example. Okay, so here's another example of a homomorphism. So I'm going to define a function from z to z mod n, and what this function is going to do is it takes an integer a and it maps it to its equivalence class in z mod n. And I claim that this is a surjective homomorphism. So let's start our proof. So I'll say let a and b be integers. What do we have? Well, I know f of a plus b. This is going to map to the equivalence class of a plus b. And by definition of addition in z mod n, we know that this is the equivalence class of a plus the equivalence class of b. And so this is just f of a plus f of b. Okay, so we have that it preserves addition. We can do the same thing for multiplication. F of a times b, this is the equivalence class of a times b. And by definition of multiplication in z mod n, this is the equivalence class of a times the equivalence class of b, which is just f of a times f of b. Okay, so I've shown that f is a homomorphism. How can I show that it's a surjection? Well, let's take any element. I'll say let k be an element of z mod n. What do we know? We know that then f of k is equal to the equivalence class of k. Okay, and k is an integer. So I could say hence f is a surjection. Right, the idea is I want to show that any element of z mod n comes from some integer. So in particular, 0 is going to come from the integer 0. The equivalence class of 1 is going to come from the integer 1. The equivalence class of 2 is going to come from the integer 2. Okay, so this is a surjection. One thing to note is this is not an injection. This is not an injection. And why is that the case? Well, I know that f of 0 gives the equivalence class of 0, and I know that f of n, this is the equivalence class of n, but since we're working in z mod n, n is equivalent to 0 mod n, this is the equivalence class of 0. So the idea is that I have f of 0 is equal to f of n, but the integer 0 is not equal to the integer n. Okay, so this is an example of something that is a surjective homomorphism, but it is not an injection. Okay, and finally, I'd like to give an example of something that just plain old isn't a homomorphism. So consider the function f from r to r given by f of x is equal to x squared. So this is just our standard function you would see in high school algebra, the parabola. And I claim that this is not a homomorphism. So in order to show something is not a homomorphism, it's enough to provide a counterexample. So let's look at this. If I look at f of 1 plus 1, this is f of 2, and I know that this is going to be 2 squared, which is 4. And if I look at f of 1 plus f of 1, this is going to be, well, f of 1 is 1 squared, plus f of 1, that's also 1 squared. So this is going to be 2, and I know that 4 does not equal 2. So I can say that f of 1 plus 1 is not equal to f of 1 plus f of 1. So I know that this function is not a homomorphism. So we're finally ready to discuss some properties of ring homomorphisms, and these are properties that are going to hold for all ring homomorphisms, satisfying the conditions of our theorem. So I'll say first let R and S be rings, and let f from R to S be a homomorphism, and take A and B in R. So what properties does f have? Well, the first thing we could write down is the 0 element of R maps to the 0 element of S. So this is true for every homomorphism. F of 0R is equal to 0S. We'll show that f of negative A is equal to negative f of A. So additive inverses map to additive inverses. We'll show that f of A minus B is f of A minus f of B. And we'll show that the image of f is a subring of S. So the subset of S that f maps R onto is going to be a subring of S. We'll also show that if R has identity and if f is a surjection, we get two additional properties. The first is that S has identity, and the identity is going to be f of 1R. So if R is a ring with identity and we have a homomorphism from R to S, which is a surjection, then the identity in R maps to an element of S, which will be the identity of S. So we don't need to assume a priori that S has identity. It's a consequence of the existence of a homomorphism. And we'll also have that if U in R is a unit, then f of U inside of S is also a unit. So homomorphisms will map units to units. Again, the homomorphism has to be a surjection, and the ring R has to have identity for this to be true. So let's start our proof of this. So let's prove these properties one by one. So I'll start with property 1. So let's examine f of 0R. Well, I know 0R can be written as 0R plus 0R. And since it's a homomorphism, I can write this as f of 0R plus f of 0R. Okay, so when I look at this equation, I know f of 0R is some element of S, but what else do I know? I know that I can write the left-hand side as f of 0R plus 0S. I can add the 0 element of S to this, and this is going to equal f of 0R plus f of 0R. And we proved earlier that rings have a cancellation law for addition, so I can cancel these two out, and what am I left with? I'm left with 0S is equal to f of 0R. So that's our property of part 1, or proof of property 1. So property 2 is also pretty straightforward. I know that additive inverses are unique, so when I look at an expression like f of a plus x is equal to 0, this has a unique solution, and we've named that solution negative f of a. It's the additive inverse of the element f of a of S. Okay, we also have, if I look at f of a plus negative a, this is going to be f of a plus f of negative a. And on the other hand, this is equal to f of 0R, which is equal to 0S. So I know that hence, I know that f of negative a also solves this equation, f of a plus x is equal to 0S. And so by uniqueness, it has to be that f of negative a is the additive inverse of f of a. So that gives us property 2. For property 3, well, let's take a look at this. I know that f of a minus b, this can be rewritten as f of a plus negative b, a plus the additive inverse of b, and this is going to be, since f is a homomorphism, it's f of a plus f of negative b. By 2, I know that f of negative b is negative f of b, so we know that this is f of a minus f of b, and this is going to be by property 2. Okay, so that proves 3. For property 4, we'll use the Subring test. So for the Subring test, I need to check that the image is non-empty, that it's closed under subtraction, and that it's closed under multiplication. So first, I know that the image of f is not empty, since, well, I know that f of 0r is equal to 0s, and this is thus in the image of f. Okay, so I know that this is not empty because f of 0r is an element of the image of f. So for the Subring test, I'm going to let f of a and f of b be elements of the image of f for some a and b and r. Okay, so let's check our conditions. I need to show again that if I subtract 2 elements of the image of f, then I have something that's in the image of f, and if I multiply 2 things in the image of f, then I have something that's in the image of f. So if I do f of a minus f of b, well, we've encountered this already. By property 3, this is f of a minus b, and this is in the image of f since a minus b is in R. We know that if a is in R and b is in R, then a minus b is in R. Also, I know that f of a times f of b, well, since f is a homomorphism, this is f of a times b. This is in the image of f, since a times b is in R. R is closed under multiplication. So I can say that by the Subring test, and if you need to recall the Subring test, this was proved in the last video on subrings, the image of f is a subring of S. So this guy is going to be a subring of S. Okay, so that proves property 4. For properties 5 and 6, we're going to assume that R has identity 1 sub R and F is a surjection. So for property 5, I'd like to show that the identity element in S is actually F of 1R. So what I want to show that if S is an element of S, then S times f of 1r is equal to s, and f of 1r times s is equal to s. That's what it means to be the multiplicative identity inside of S. Okay, so let's prove this. So I'll say let S be an element of S. Since F is a surjection, so since F is onto, there exists an R in R, so there exists an R in R, such that f of r, f of little r, is equal to little s. Okay, so let's see what this gives us. Well, I know that s times f of 1r, this is now f of little r times f of 1r. Well, this is a homomorphism, so this is going to be f of r times 1r. Well, r times 1r is just r, so that's f of r, so this is equal to s. Similarly, if I swap their order, f of 1r times s, this is equal to f of 1r times f of little r. So this is f of 1r times little r, because f is a homomorphism. 1r times little r is just little r, and this just gives me s. So I've shown that f of 1r is the multiplicative identity inside of S. Okay, and we're finally ready to prove property 6. So if u in R is a unit, so if I take a unit, then there exists an element u inverse inside of R such that u times u inverse is equal to 1, and that's also equal to u inverse times u. Okay, so let's use this to our advantage. Well, what do I know? I know that f of 1r, I know that this is equal to 1s. Or rather, this is the multiplicative identity of s, which we can call 1s. Okay, well, this is going to be f of u times u inverse, which is going to be f of u times f of u inverse. Okay, so I've shown that f of u is invertible from one side, and I can do a similar computation and say 1 sub s is f of 1r. So this is f of u inverse times u, which is f of u inverse times f of u, right? So I've shown that f of u times f of u inverse is going to be 1 sub s. That's what we'll call the multiplicative identity inside of s. And this is equal to f of u inverse times f of u. Hence, I've shown that f of u is a unit. F of u times some element of s is equal to 1, is a unit. And namely, what element am I multiplying against f of u? It's f of u inverse. That's what gets me to 1. And moreover, the inverse of f of u is f of u inverse. Okay, so that proves property 6, and that gives us all the properties that we need for now. So the last few examples are going to involve what's called the Cartesian product of rings. And what we're going to do is we'll take R and S, they're two rings, and we're going to look at the set R cross S, the Cartesian product of R and S. So this is just a set of all ordered pairs R comma S, where little r is an R and little s is an S. And we can give this a ring structure by doing the following. We'll say that R1 comma S1 plus R2 comma S2 is, well, we'll add the R components, we'll add the first components, and we'll add the second components. So the sum is R1 plus R2 comma S1 plus S2. For multiplication, how do I multiply two ordered pairs? Well, we'll say that we multiply the first components and we multiply the second components. Okay, so the important thing to note about this is that this gives R cross S a ring structure, and it's a ring structure whose zero element is 0r comma 0s. And it's a good exercise to actually check that this is a ring. So it really forces you to go through all the ring axioms one by one. So it's a good exercise to kind of do this manually. It's quite tedious, but it is good practice with the ring axioms. If R and S have identity, then R cross S will also have identity. And so if one R is the identity in R and one S is the identity in S, then the identity element in R cross S is just 1R comma 1S. It's this ordered pair. And again, it's a good practice to check that this all checks out. One thing you can also show is that if R and S are commutative, then R cross S is also commutative. And it's also interesting to think about, if R and S are integral domains, is it true that R cross S is also an integral domain? And the answer to that is going to be no, but it's a matter of producing a counterexample, assuming that R and S are non-zero, that is. Okay, so let's look at a quick example of this kind of structure, and then we'll try to determine what some of these rings that we study are going to be isomorphic to. Okay, so the first ring we're going to study is Z2 cross Z3. And this is the elements of Z2 cross Z3 are things of the form A comma B, where A comes from Z2 and B comes from Z3. So the elements here are 0, 0, 0, 1, 0, 2. 1, 0, 1, 1, 1, 2. So this is a ring with 6 elements in it. And let's do a few examples of arithmetic just to kind of get comfortable with this. And we'll talk about what this ring is actually isomorphic to. So for example, if I were to do 0, comma 0 plus 1, comma 2, what I end up doing is 0 plus 1, comma 0 plus 2. I get 1, comma 2. All right. In general, the 0 element of Z2 cross Z3 is going to just be 0, 0. Right, I can check that 0, 0 added to anything is that same anything. Okay, so what if I were to do something like 1, 0 plus 1, 1? Well, what am I doing? This is going to be 1 plus 1, comma 0 plus 1. And the thing that I would notice here is that this first addition takes place in Z mod 2. The second addition takes place in Z mod 3. So 1 plus 1 is 2, and 2 is 0 in Z mod 2. 0 plus 1 is 1, and 1 is just 1 in Z mod 3. Okay, so I get something that looks like this. I can also do something like 1, 1 plus 1, 1. So this is going to be 1 plus 1, comma 1 plus 1. And again, 1 plus 1 in Z mod 2 is 0. 1 plus 1 in Z mod 3 is 2. All right, so the first entry, the addition is taking place in Z mod 2. The second entry, the addition is taking place in Z mod 3. Okay, what else can we do? We can do something like 1, 2 plus 1, 2. I notice that this is going to be 1 plus 1, comma 2 plus 2. I'll see that, well, 1 plus 1 in Z mod 2 is 0, and 2 plus 2 is 4. 4 in Z mod 3 is the same as 1, so this is going to be 0, comma 1. Okay, so this is how these operations look. There's also a similar thing for multiplication, so we could multiply elements of these two rings. So for example, I can do 0, 1 times 1, 2. What is this going to look like? Well, I multiply the first entries, I do 0 times 1, and then I multiply their second entry, so 1 times 2. So I'm going to get the element 0, 2. Right, 0 is the first entry, 2 is the second entry. I can do 1, 1 times 1, 2. This would be 1 times 1, 1 times 2, and this is going to be 1, 2. I can do other types of stuff. I can do something like 0, 2 times 1, 2. So what is this going to be? This is going to be 0 times 1, comma, 2 times 2. And what is this? 0 times 1 is 0. 2 times 2 is 4, but 4 mod 3 is 1, right? So I get a ring structure given by these types of operations. So this is just an example of this kind of Cartesian product of rings. The whole idea is that the operation in the first entry is taking place in Z mod 2. The operation in the second entry is taking place in Z mod 3. Okay, so let's study this ring a little bit further. Okay, so the first thing I'm going to show is that this ring Z2 cross Z3 is actually isomorphic to Z6. So Z6 and Z2 cross Z3 have the same ring structure. So how are we going to prove this? So first, let's start an investigation. Before we prove anything, let's use some of our properties and start an investigation. So the first thing I'm going to do is I'm going to suppose that f from Z6 to Z2 cross Z3 is an isomorphism. Suppose I have some sort of isomorphism. Well, what kinds of things need to be true? I know that if it's an isomorphism, it's a surjective homomorphism. So I know that 0 needs to map to 0, and that the multiplicative identity in Z6, namely 1 in Z6, needs to map to the multiplicative identity of Z2 cross Z3, namely 1, 1. So one thing I know is that f of 0 must be 0, 0, and f of 1 must be 1, 1, right? The idea is that 0, 0 plus ab is always equal to, well, it's 0 plus a, 0 plus b, so it's ab. So we see that 0, 0 is the additive identity in the ring Z2 cross Z3, and I know that 1, 1 times ab, this is going to be 1a, 1b, which is just a comma b. So I see that 1, 1 is the multiplicative identity. And we showed that surjective homomorphisms have to map one element to one element. They have to map multiplicative identities to multiplicative identities, and all homomorphisms have to map 0 to 0. Okay, so we have this. But what are we forced into when we have this kind of thing? Well, let's look at f of 2. I know that 2 is 1 plus 1, so I know that this is going to be f of 1 plus f of 1. So that's 1, 1 plus 1, 1. This is better known as 2, 2, which, if I'm looking in Z2 cross Z3, the first entry becomes 0 because 2 mod 2 is 0. The second entry stays as 2. Okay, so I have this function that takes 2 and maps it to 2, 2, or if we simplify it in Z2 cross Z3, it's 0, 2. What about f of 3? F of 3, well, this is f of 1 plus 2. So it's going to be f of 1 plus f of 2. And what is this going to be? This is going to be 1, 1 plus 0, 2, also known as 2, 2. So I'm writing it as 2, 2 for a reason. We see that this is 3, 3. And what is 3, 3? Well, if I'm working in Z2 cross Z3, 3 mod 2 is 1, 3 mod 3 is 0. So I get 1, 0. If I look at f of 4, you can probably see where I'm going with this. F of 4 is f of 2 plus f of, well, it's f of 2 plus 2. And since this is a isomorphism, this is f of 2 plus f of 2. What are we going to end up with? We're going to end up with, well, 2, 2 plus 2, 2, which is 4, 4. And 4 mod 2 is 0, 4 mod 3 is 1. So I get 0, 1. And you can imagine we can continue this way. F of 5 is going to be 5, 5. So this is going to be, well, 5 mod 2 is 1, 5 mod 3 is 2. And that's going to be it, right? Because the elements of Z mod 6 are 0, 1, 2, 3, 4, 5, right? They're those equivalence classes. And the thing to notice is that this map is an injection and a surjection, right? The key idea here is that I've hit every single element of Z2 cross Z3, and I've hit every single element exactly once. Okay, so I have this surjection, and I might notice that the map that I'm defining is that f of a is equal to a comma a, and then I'm reducing mod 2 in the first entry and mod 3 in the second entry. Okay, so we have that this thing is a bijection. Right, we have that this map is a bijection. Now let's check that this is actually a homomorphism, so that we have that we're actually dealing with an isomorphism here. Okay, so now we can check that we're actually dealing with a homomorphism here. So our function that we just found from z6 to z2 cross z3, we took a and we mapped it to a comma a. And now I'm going to use this equivalence class notation. So this is just saying a modulo 2, and this is just saying a modulo 3. So I'm going to use the subscript 2 to indicate mod 2, the subscript 3 to indicate mod 3. And so what's the idea here? Well, we just checked that this function is a bijection, right? We just constructed this function. We checked that it's a bijection. Let's check that this is actually a homomorphism, because we want to make sure that it preserves addition, and we want to make sure it preserves multiplication. So let's check that it has those properties. So I'm going to say let a and b be elements of z mod 6. Okay, so then what do I know? I know f of a plus b, by definition, it's the equivalence class of a plus b mod 2 and the equivalence class of a plus b mod 3. What do I know about these? Well, I know by definition in z mod 2, this is the equivalence class of a plus the equivalence class of b. And I know by the definition of addition in z mod 3, this is the equivalence class of a mod 3 plus the equivalence class of b mod 3. What does this equal? Well, this guy right here, this is, by definition of addition in Cartesian products, this is a comma a plus b comma b. So this is b mod 2, b mod 3. But what is this? This is nothing more than f of a plus f of b. Okay, so we've shown that f of a plus b is f of a plus f of b. And now let's check multiplication. So if I look at f of a times b, this is going to be the equivalence class mod 2 of AB and the equivalence class mod 3 of AB. Okay, by definition of multiplication of equivalence classes, this is the equivalence class of A mod 2 times the equivalence class of B mod 2, and this notation's a bit cumbersome. This is the equivalence class of A mod 3 times the equivalence class of B mod 3. And by definition of multiplication in our Cartesian product ring, this is the equivalence class of A mod 2, comma the equivalence class of A mod 3, times the equivalence class of B mod 2, comma the equivalence class of B mod 3. But what is this? This is just f of A times f of B. So hence, f is an isomorphism. All right, we checked it's a bijection earlier. By construction, it was a bijection, and we just checked that it satisfies the, well, it preserves our addition and it preserves our multiplication. Okay, so Z6 and Z2 cross Z3 have the same exact ring structure. They're the same ring, just labeled differently. Here's another interesting example. So we're going to show that Z4 is not isomorphic to Z2 cross Z2. Okay, so let's check this. I'll say suppose that Z4 is isomorphic to Z2 cross Z2. Suppose that we do have an isomorphism. So I could say then there exists some isomorphism, so a function f from Z4 to Z2 cross Z2, which is an isomorphism. So this is a operation preserving bijection, so which is an isomorphism. Okay, so what do we know about this isomorphism? We know that f of 0 must be the 0 element, and since Z4 has a multiplicative identity, we know that Z2 cross, well, and we know Z2 cross Z2 has a multiplicative identity, so they must map to one another as well. But we run into a problem pretty quickly, right? We're going to notice that f of 2, if this is a isomorphism, this has to be f of 1 plus 1. So this is f of 1 plus f of 1. And what do we end up with? We end up with, well, 1, 1 plus 1, 1. And so we end up with 2 comma 2, but this is 0 comma 0. So what's the problem here? The problem here is that f of 0 is equal to 0, 0, which is the same as f of 2, but 0 does not equal 2. So F is not an injection. And this is a contradiction, because we assumed that it was an isomorphism, and hence it must be a bijection. Okay, so we see that no isomorphism can exist, right? If we assume an isomorphism exists, we run into a problem. We run into a contradiction. Okay, and finally, I'd like to end with 2 more examples. So the first example is that Q is not isomorphic to Z. So this one is interesting because there are bijections between Q and Z. It just happens that none of those bijections are ring isomorphisms. And now the question you might ask is, well, why is that true? Well, the thing we might remember is that if we have an isomorphism, namely if we even have a surjective homomorphism, but in particular an isomorphism, this function is going to have to map units to units. And if it's an isomorphism, it's going to do so in a one-to-one way. And the problem here is that Q has infinitely many units. Every non-zero element of Q is a unit, and Z only has 2 units, namely 1 and -1. So it's impossible to map all the units in Q to units in Z in a one-to-one and onto way. Okay, so this is kind of interesting, like I said again, because there are bijections between Q and Z, it's just that none of them are ring homomorphisms. Okay, the other interesting example is that Q is not isomorphic to R, and it's actually for the opposite reason. The reason is that there are no bijections between Q and R. So Q is countably infinite, and R is uncountably infinite, and we have arguments that show that there cannot exist a bijection between Q and R. So these cannot be isomorphic as rings.